Okay, so welcome to today's video. Today we're going to be talking about finding out the boot time latency for nanos. This actually came up as a question. The student, I believe he's working on a paper of some kind. He was asking about cold start times and wanting to compare them to other unikernels. Um, Basically, he suggests this, using time, ops package to load. Basically, state that there's multiple problems with that method. Your timing, when you time ops package load, what you're really doing is timing both the creation of the image and running of the image. And even if you take out the image creation part, you're still, timing ops itself, which is kind of a convenience tool when ran locally, because what it really does is it just spawns a new QEMU process, and that's probably what you really want to be looking at. So we kind of get into how to do this. Now, before we kind of get started, I just wanted to point this out. If you're on Ubuntu or Debian, or I think even Arch has this issue, for some reason the binary build of Perf, which is the tool that we're going to be using, is missing libtrace event. So if you just do like a sudo apt-get install, the Perf or Linux tools or whatever it is, you're going to be missing this component, which sucks, right? So what you're really going to want to do is go to kernel.org and download something that's relatively the same kernel version as you have, which for me, it was Linux 6.2, and you're just going to want to build perf from source, so it has this libtrace event. Okay, so now we got our tool. Now what? Well, let's pop into the shell here. When you're tracing, what we're going to be doing is we're going to be writing to this port at OXF4. And then the value that we're writing out to it is basically going to indicate where we are in the boot time. And so we try to start at stage one. Very first thing, we start there to kind of write out our first event. And so we're just giving it the number 10. And then down here, the very first time we get into our user program, we're going to log out again, and here we're going to set the value 200. So basically what we're going to do is we're going to record the execution of QEMU booting our kernel and into the user program, and then we're going to look for these two values, 10 and 200. So you really only need these two changes. If you want to trace more events, just give it another number, and that'll kind of tell you where you are in the execution. Let's see here. Okay, and then I took this script, this rec.sh. I took it from this blog post, and it's 2024. This was written in 2019, so some of this stuff doesn't quite work. In fact, the Python I was mucking about with, and I decided to just not even use the Python that he has here because I didn't really need it anyways. But yeah, essentially you still want to grab this repo, yank this down. As you can see, I'm in there. And then this rec.sh is what we're actually going to run. So our perf command is perf kvm record. We're going to capture kvm entry and PIO and the schedule process exec events. And the QEMU command we're running is this. You're probably wondering where I got this. Well, let me just show you real quick. I think, so this is the program that we're actually going to run here. So it's pretty basic, right? We just say test, then we say, we sleep for 10 seconds, and then we say done. So pretty basic. Basically, I do an ops run main, And then when you do ops run main, if you do like a pxox grep for QEMU, you'll see the QEMU command. Just cut and paste that command, and this is what it's going to be. And so our ops image, because the program was named main, that's here as main. Yeah, and so that will record it. So let's go ahead and do that real quick. We're gonna do a rec sh. So it's booting it up, and it's using Perf to record everything. As you can see, it grabbed an IP address, did my test message, all this sort of stuff. Our script waits for, a few seconds. And as you can see, it's kind of exited, woken up 13 times to write data, yada, yada, yada. This is our file here. And then what we want to do, let me see if I have this command here. Yeah, okay, so now we're gonna do this perf script -I for QEMU perf data, and we're just gonna turn it into plain text, because this guy is binary. So we can kind of take a look at what that looks like. Basically all these various events. This is seconds, and then the dot is your microseconds. So that's how you measure it, right? And what we're going to do is we're going to basically look for this port. So I got my grep of OXF4. We're going to grep out anything that got written to that port. And as you can see, we have our two events here. So this is the first one. So 10 to hex is OXA, and then that 200 is OXC8 in hex. And what we can do is we'll do this minus this, times it by 1,000, because 1,000 microseconds, milliseconds, and we get about 62 milliseconds boot time. So not too shabby. Now some of you guys might be thinking, I read some unikernels can boot in 10 milliseconds. And you're right. There are projects out there that advertise getting in under 10 milliseconds. However, I would like to point out a few things. There's a lot of projects out there. Like, in fact, I would say your average project can't actually take advantage of this. Whether it's 100 milliseconds or 60 milliseconds or 10 milliseconds, there's kind of a diminishing returns as that number goes down, because when you think about it, your average, I don't know, whether it's a Go project or a Python project or Java or, whatever it is, if you think about it, like your average application takes more or less a few seconds minimum for like an actual boot, like a real boot time. What I'm talking about is like if you have a web server, it has to connect to a database. Maybe it's loading some static assets from disk. Maybe it's, I don't know, doing all this other kind of initial setup. And so that initial setup almost always takes longer. I mentioned Java. Like, there's not a single Java program out there that doesn't take like a while to boot, like Elasticsearch or something like that. You're just not going to benefit from shaving off, 10, 15 milliseconds or whatever. Second off, when you see stuff where it says, oh, we're booting in 10 milliseconds, you need to understand that somebody's kind of gone in and optimized the hell out of the kernel and or the application itself to achieve that result. It's not something that you're just going to get out of the box and expect it to work everywhere. So whether it's, the various page tables being set up, or whether it's various drivers that are not present, or, there's lots of little things that you might actually need and want, and yet they took out to show you that number. So you need to understand that that's, it's not something that you should expect to see on everything. Furthermore, this is the third point, is that when you have an application, most real world applications, forget their boot time. let's just talk about their runtime. Most real world applications don't spin up in seconds and then spin back down in seconds, because that's just not a realistic workload, right? Realistic workloads, you kind of have two varieties. One, you have a persistent service. So like think of a web server that just sits there and runs day after day after day. You don't want it to spin down. And then number two, like maybe it's a cron job. So it does spin down after it does its work, but like, most of the cron jobs I see, like whether it's running like a marketing report for, marketing or something every night at 11 p.m. or something like that, it might take minutes to run the damn SQL query, right? So it's not going to benefit from like shaving off 20 milliseconds or whatever. So I think the real world use cases for getting these obscene boot times is actually relatively low, is what I'm kind of getting at. Yes, it's better than 1 second, but after a while, I just don't see benefits from trying to shave every, millisecond out. Anyways, this is a long-winded way of saying, if you want to measure the boot time, you can use Perf, and this is how you do it. Until next time.